Okay. So we'll be doing kind of the last new material today. I updated the slides on Canvas for week 5, so there should now be about another 15 to 20 slides at the end. That's what we'll go through today. I think we'll get through it with a little bit of time left. If we do that, I'll do some practice exam problems. On YouTube yesterday and the day before, you'll kind of notice I have 3 kind of shorter videos here. They go over small sets of questions. On this one here, I added in a question that wasn't on the practice exam that would be something that you could see on the exam. Just if you have specific questions as you're working through that, you can kind of watch these videos, watch me work through it. The ones that aren't here, so kind of the 11 through 16, and then the ones prior to question 5, we can do those. I'll probably start on some of those today in class. Or those will be ones that we cover on Monday, where I'll just be going through questions from either one of those practice exams that you guys have specific questions on. Once we do that, I'll probably, even today, if we do a couple at the end, I'll kind of cut that video up from the lecture and kind of post that as well. So if you have a specific question, it's a little bit easier to find it in a small video as opposed to like me just taping one long video of me working through the entire practice exam, okay? That exam will be on Canvas. Early Monday morning. You can take it at any time. Like I said, probably waiting till maybe we do the review might be a good idea. So anytime Monday after class or anytime on Tuesday, you can start it as well. Once you start, you'll have 80 minutes, hour and 20 minutes to kind of complete it. It will be found under the quizzes tab. So you'll have all your online quizzes. You can kind of see here, that's going to be what it is. The unnamed quiz is actually going to be exam number 1. So once I get that posted, it'll be under the quiz tab, but I'll create like another kind of category that'll say exam on it. So it'll be very clear that this is the exam. Okay. Any questions from me before we kind of jump into the material today? Let's see if you can chat. Okay. All right. So we've talked about discrete random variables. We're going to introduce the idea of a continuous random variable today. We're going to talk about one very specific continuous random variable, and that will be the only continuous random variable that we see on the exam. We'll kind of keep dealing with it after the exam, but just one specific one. So, this is just a review side. We've looked at this a couple different times, right? We're now going to be dealing with a variable where we can see values in between the integers, right? I've shown you this slide, I think this is like the 3rd or 4th time now, right? Just introduce this idea of a continuous variable. So we're dealing with a continuous random variable, right? It's going to have its own distribution. And just like with the Poisson or the binomial, it's going to have its own probability density function, okay? So this probability density function with a continuous random variable is going to be a little bit different. The probability of any one value, you think about this in the most simplest of terms, right? If I have an infinite number of values, and let's just say for now they're all equally as likely, because if it is truly continuous, and I could see any value, in between 0 and 1, there's an infinite number of numbers. So let's say every outcome is equally as likely, so 1 over the number of outcomes. Well, if the number of outcomes is infinite, 1 over infinity, and the limit actually approaches 0. So the probability of any one specific value, if it's truly a continuous random variable, is 0. And the probability density function can only tell us the probability over certain intervals. So it can tell us the probability between 0.5 and 3, or between 0.1 and 0.2, but it can't give us the probability of exactly one number, because if it's truly continuous, the probability of any one specific number would end up being 0. Okay? So it's a little bit different than the discrete. We can still show this with a table or graph. In fact, I'm not going to make you do this in this class, but we can start to almost think about this probability density function. We wanted to integrate it over certain intervals. Essentially what we'd be doing is finding the area below this curve, right? Because now it's no longer just a bunch of bars, it's truly continuous, so it's this nice continuous line. And we could find the probability over those intervals. So I just want to skip ahead here for a second to give you a visual, right? So quite often, we're going to be dealing with a normal distribution or something that looks like this. So now it's continuous, right? This is what we're going to be dealing with, right? Some of the properties, there's not going to be any jumps, right? So this is a nice continuous line. This is a function that doesn't kind of jump, you know, at 3, the probability doesn't go from 0.9 and jump all the way up to, you know, or sorry, 0.1 and jump all the way up to like 0.3, right? It's this nice continuous line. For any value over that sample space, the probability density function has to return to us a 0 or a higher value. It's still a probability, so it's still between 0 and 1. And then if I integrate over that entire probability density function, the area under my continuous curve, right, that represents my distribution will always be 1. Because now you almost think about it as the area under that curve really represents the entire, every single possible experimental outcome and the probabilities. So if I was to say, take this probability, add them all up, I'm adding up all the probabilities of every possible outcome. We know that just always sums up to 1, right? Even with the discrete examples, if we added up the probabilities of every possible outcome, they added up to 1. So I know they do this in calculus class where, like, even if you have a continuous line, you could like think about it as all these really small rectangles. And then if you added the area up of all of them, it would give you the area under the curve. You can think about that here, and that area under the curve will just always be 1. Okay? Yeah, so I kind of already mentioned all that. So if we think about the y-axis here kind of representing probability still, it's almost like, you know, before we're discrete, we would have like bar graphs. Now we've just got this nice continuous line. The area under that curve will always be 1. Okay? So that's where we're kind of starting off. So area under this curve is 1, right? We can do the cumulative density function. I'm not going to waste too much time on this because this isn't completely relevant to what we're going to talk about today, but more so next, kind of after the exam. You can kind of imagine that as I want the cumulative density, as I move to higher and higher values, that area under the curve is going to get closer and closer to 1. And as I go to really small values, the area is going to get closer and closer to 0, right? These are things we've already talked about with this cumulative density function. Like I said, I'm going to kind of skip over this for now because it's not really relevant to what we're talking about today. Okay? So if I want, say, the probability x is less than a certain number, we'll call that number A. I find where A is. What's the probability I see x be less than or equal to A? Well, it's, once again, you could think about there's a bunch of really tiny rectangles here. If we added them all up, it'd be the area under the curve, but lower than A, right? So the area under the curve, but less than A. Right? We want to, and kind of the way that we would write that, if we were using the cumulative density function, would be this capital F of A, right? Because we're finding the probability of A and everything to the left of it. Right? We've dealt with this idea of cumulative with distributions before, but before the distributions weren't continuous, they were just kind of a few rectangles here. Right? We'd start in the value we're interested in and add up all the probabilities below it. That's really what we're doing here. It's just the probabilities below it are these really small rectangles, right? Well, that's how we can think about them. If we wanted the probability that it's greater than B, we would plot B, find all the values that are greater than B under that curve, right? Add up all those probabilities. Another way of writing that is we could do 1 minus the cumulative density function, right? So the cumulative density function would tell me the probability that's less than B. If I want the probability that's greater than, just 1 minus. Like I said, we won't be dealing with this too much today, this kind of notation of the cumulative density function, so I wouldn't worry too much about this. Focus more on just thinking about the visual here. Okay? But one of the probabilities between A and B, plot A and B, all the outcomes, all the values in between those two values, area under the curve. Right? Once again, we could write this using cumulative density functions. Don't worry about that. We're not doing any of that for the exam, so this will be stuff that I kind of revisit next week after the exam. Just focus on the visual here. You know, I could think about the area outside of A and B. I could do a bunch of different combinations here, right? It's just really what outcomes am I looking for, and then the area under the curve. Okay. All right, so that was just kind of a precursor, just generally thinking about these continuous distributions. We're going to talk about a very specific one that isn't normal, but in fact is a little bit easier to deal with than a normal distribution. Okay. So this is going to be the uniform distribution. So in a uniform distribution, every equally sized interval or kind of length that we're looking at is going to have the same probability. So the probability that I see values between 1 and 2, that's going to be the same as the probability that I see values between 3 and 4. Right? And when I say 3 and 4, remember, it's every value in between now because it's continuous. Okay? So if, let's say, we had the probability kind of here, f of x, or the probability on our y-axis, all the different possible values for x. Right? Let's say the probability that I'm between 1.5 and 2.5. Right? I don't know what that would be, but we could plot it here. So it's like right there. It would have to be the same as the probability that we're between. Oh, that doesn't quite line up on it. 3.5 and 4.5, right? Equally sized intervals have the same probability of occurring. So what's going to end up being true is our continuous random variable, if it's uniform, isn't this like bell-shaped curve. It's literally just a straight line. Because if we took any equally sized interval, it would have to have the exact same probability of occurring. Okay? Let's go back here. But kind of where does it start and stop? So where it starts and stop, here I've notated just as C and D. You can think about this is our min and our max, right? Or our minimum and our maximum. So I don't have to keep switching over. Let me just make this a little bit bigger and we can see us at the same time. You guys in person can see me. But basically, this is just going to go down to whatever my minimum is. So we'll call that 0 here. And this will just go up to whatever, let's say goes up to 10, goes up to my maximum. The notation I can use in the slides here, this was C, this was D. Okay? But if you wanted to just write in there, your min to the max. Okay? So this density function, if we think about this way, if I have 10 possible outcomes and they're all equally as likely, what's the probability any one outcome occurs? 10 possible outcomes, all equally as likely. If I was dealing with a discrete random variable. 1 over 10, right? Yeah. If I have 100 possible outcomes, 1 over 100. But the 1 over 10 kind of makes sense with these numbers I've used because if we think about, well, the probability that I see something between, 1.5 and 2.5, that's just like a block of 1. So it's almost like we can kind of think about this as like a discrete. It's just 1 over n. The problem is our n now is whatever the range of our data is, right? From the maximum to the minimum. So if I go from 0 to 10, I have 10 equally sized kind of rectangles in there that all would represent an interval of 1, right? 0 to 1, 1 to 2, 2 to 3. I would have these kind of 10 equally sized areas. And if I have 10 equally sized areas, probably that they're all the same, probably occurring 1 over 10, right? If I was to break up from 0 to 10 into 100 different areas, right? Well, then the probability of any one of those areas occurring would be 1 over 100. And I think I can split it however many ways that I wanted to, right? But I'm still dealing with the range from 0 to 10, okay? So this density function, we'll say that the height of it will just be 1 over d minus c. Here are d and our c are 10 and 0, or 1 over the maximum minus the minimum, right? That's going to tell us what the height of that uniform distribution would be. I think this will make a little more sense in just a second once we get to thinking about how we find probabilities over certain intervals. So if I then wanted, okay, what's the probability that I see a value from 1.5 to 2.5, right? So I want the probability that I see a value between 1.5 and 2.5. Well, remember when we had the normal curve, it's just the area in between those two values under the curve. Well, our curve is a straight line now, but it's still the area under that curve. If I'm looking at this, how could I find this probability? What is this? Shape. It's not drawn perfectly, but this is a rectangle, right? So really, I'm just wanting to find the area of a rectangle. How do I do that? Well, what's the, you could call this whatever you want. Length times width, base times the height, right? But I can take this side of my rectangle, which I know is just the height of my uniform distribution, or 1 over the maximum minus the minimum. And I could then multiply that by whatever the length of my interval is. Here it's 1, but if we call A the beginning of that interval and B, the end, right? Those were the two values I was interested in. Notice this kind of length would just be B minus A multiplied by, what's the height? 1 over, and we said D was the maximum, C was the minimum. So if we want the probability, get rid of this here for a second, of seeing values in between any, A and B we're choosing, right? But to find the probability that we're between these two values, right? B minus A times 1 over D minus C, we can also write that as B minus A divided by D minus C, right? And really, if you want a better way to think about this is, here, let me write this up here. That's the kind of like formal. What I would say is, think about if you want the probability of being between any two values, A and B, what you're really going to do is say the end of the interval you're interested in minus the beginning. I'm running out of room, but beginning of the interval, right? And then you'll divide that by max of your distribution minus the minimum of your distribution, right? You could write it out that way so you don't have like A, B, D, C. It's end of my interval minus beginning of my interval divided by maximum of the distribution minus the minimum of the distribution. And the reason why that always works out is because the height was 1 over the maximum minus the min. So my height of that rectangle will always be 1 over maximum minus the minimum. And the length will always just be, well, what two values am I interested in? The range in between those two, or the difference in between those two values. Okay? So that's why it always works out to being this, okay? Like I said, you could use this equation and plug the answers in. I always think that the best way to do this is draw out your uniform distribution and then just think about the height and the length of a rectangle and multiply those two, right? Length times width. That's way easier, I think. So we'll go through some examples here and I'll kind of show you that. So let me get over here. So you can kind of see a visual here. I already drew this on the board, but here's our minimum and our maximum. So we know the height is 1 divided by the maximum minus the minimum. If we then, I'll skip ahead here. Nope, no, I won't. I then kind of showed you on the board, right? If I had A and B here, now I'm just finding the area of a rectangle. Okay? So some nice summary statistics for the uniform. These should be pretty easy. It's kind of like the binomial. We just have the equations, right? So the very first one makes sense, right? If I have a starting point and an ending point to my distribution, the mean, since everything's equally as likely, you can think about everything's equally weighted. And so the mean will just be whatever the middle value is, or take the average of the maximum and the minimum, right? Add them up, divide by 2, right? If I have 0 and 10, what should my mean be there? Just intuitively, you know, in the middle of that would be 5, right? 0 plus 10 divided by 2 is 5. What if it ranges from 50 to 60? Well, there my mean would be, intuitively, the middle number is 55. How did I get that though? 50 plus 60, 110 divided by 2, 55. So to find that mean, a lot of the times you can kind of envision what it is like in your head, but the real formal kind of formula that we should use is add up your maximum minimum, divide by 2. You really just find the average kind of your maximum minimum. Now the variance, once again, we could work through, Google the mathematical proof, walk through it. It doesn't matter what our maximum minimum are. The variance of our uniform distribution will always be whatever that range is, so maximum minus the minimum, squared and divided by 12. You can kind of walk through the proof and imagine, like, if this is the mean, and I had a function, I know the density function is 1 over d minus c. If I start to take the difference between every single x value and the mean and square it, that's kind of where this comes from. Right? Why it's 12? It's just the way the math works out. If you go through the proof, you can see it's just the way that the math will work out. Okay? But once we know that these are the equations, we don't have to do the work out that math every time. We'll just use these two equations, right? Kind of like with the binomial. It was always n times p and n times p times 1 minus p. Same kind of idea here. We get the mean or expected value using this formula. We get the variance using this formula. Any questions on this? I'm going through this stuff kind of quick so we can work through some more examples with numbers here. We're okay on this? Okay. So let's work through, I forgot to change this because this is from my old slides. This is not clickers, we're not doing clickers, this is just a sample problem, right? So let's say there's this movie, Santa with Muscles 2, it's gonna be released soon because the first one was rousing success. And we have demand for popcorn being a uniform distribution. So the way that we'll write the uniform distribution is using this U, and then the two things that it identifies is it's a uniform distribution, that's what demand is, this variable, starting from 1, ending at 10. So the minimum is 1 here, the maximum is 10, okay? So if I had this, what would the mean pounds of popcorn demanded be? Or what would the expected value be? Well, if I know the minimum of my distribution is 1, the maximum is 10, I just have to find the middle number there. So I would add them up, divide by 2, or 1 plus 10 divided by 2, or sorry, yeah, 1 plus 10 divided by 2 would be 5.5. Right? So, you know, if I think about too, the uniform distribution tells me the minimum and the maximum. 95 shouldn't make any sense here, right? That mean or expected value should be somewhere in the middle of your minimum and maximum. But the real process we use is just add those two values up, divide by 2. Find that middle number. Okay? And this is an actual, well, Santa with Muscles 2 wasn't an actual movie, but Santa with Muscles was, and it had Hulk Hogan, and it's a great, like, cringy, late 80s, early 90s video you should all watch. I don't really know where you can find it. Maybe it's on Amazon or something, you can rent it. But anyways, so let's kind of continue. So, all right, just kind of revisiting. Once I have my maximum minimum, I can just draw out my uniform distribution. It's going to be this giant rectangle representing my entire experimental outcome space. So what should the area of this rectangle be? If D is the maximum, C is the minimum. It represents my entire experimental outcome space. The area under the curve should be 1, okay? So the height of that distribution, just as a reminder, 1 over the range, 1 over the maximum minus the minimum, okay? If I then want to find the probability I'm in between two values, A and B, I said, well, we can think about this as a big rectangle, right? Take 1 over the maximum minus the minimum, multiply that by the difference of B and A, or B minus A. Right? Length times width, or height times whatever you want to call it. Right? So we had the more formal, another way of saying that, B minus A times 1 over D minus C. We could also rewrite like this, right? Because dividing by something is the same as multiplying by 1 over that. Okay? Excuse me. So let's return to this example. Right? We've got a uniform distribution, starts at 1, ends at 10. What's the probability that if the movie theater makes 9.5 pounds, that they will run out, right, of angry customers because there won't be enough? Well, the only possible way that if they made 9.5 that there wouldn't be enough popcorn is if the amount demanded is greater than 9.5, right? So what we can be thinking about here is, I'll just draw this out. Okay? So I've got, and I usually won't draw a y-axis here just for kind of simplicity. But here I know my maximum's 10, my minimum's 1. I don't know why I did my 1 that way. Hold on. There we go. Okay? I want the probability that I see demand be greater than 9.5. Okay? So this one's a little bit tricky because it's not like I told you what's the probability that demand is in between 7 and 8. I said, what's the probability it's greater than 9.5? But if I know the maximum of this distribution, where would my interval end here? At 10, right? It has to stop at the maximum. It can't be higher than that maximum. So I'm really just looking for the area of this rectangle. What's the kind of base of this rectangle? Goes from 9.5 to 10, so we'll take that. And then we have to multiply by the height of that rectangle, where the height of the uniform distribution was 1 over max minus min. So here 1 over, I don't know why sometimes I write my 1s 1 over. Okay. 1 over 10 minus 1. Right? So I'll then multiply this by what? 1 over 10 minus 1. So 0.5 times what? 1/9. So it's as simple as that. I think drawing it out really helps. Like once you identify where your interval is, it's very easy to see where it starts and stops. You'll take the difference between that. That's the length of the interval you're interested in. Multiply that by the height of that rectangle, which is just 1 over the maximum minus the minimum. Okay? Any questions on that? What if I wanted the probability that it's between 4 and 8? What's the only thing I would really have to do differently? Yeah, right? The height remains the same. My maximum and minimum didn't change. So just find the length of whatever interval I'm interested in. Okay? Now, if I for some reason switch those, like let's say, you know, I did this. Why do I know I'm going to be wrong? My answer is going to be negative. What am I looking for? I'm looking for a probability. It has to be between 0 and 1. Now, it'll be the right value. It'll just be negative instead of positive. But, you know, if you flip those around, hopefully it's pretty easy to identify like, oh, yeah, what was I doing? Like I have to take the higher number and subtract the small number. Any questions on that before I keep moving? Let me see. Make sure there's not anything in the chat. Okay. All right. And there's, I guess, some movies taken from that, or pictures taken from that movie. So we kind of already did all this up there on the board. You know, if we actually kind of write that out using the more formal way, which you can, like I said, I just think drawing it and kind of grabbing your numbers from the drawing is a lot easier than finding the area of a rectangle, right? What if I wanted the probability that exactly 9.5 pounds of popcorn is demanded? What should that probability be? I said something earlier. I said if it's a truly continuous random variable, even between 1 and 10, how many possible outcomes could we see? An infinite, if it's truly continuous. So let's say I wanted to find the probability of exactly 9.5, and I try to draw this out. Okay. So get rid of this area. So let's say I want the probability of exactly 9.5. So what would my interval start and stop at? 9.5. So when I think about the kind of width of my rectangle, what is it? 9.5 minus 9.5, it would be 0. 0 times any uniform distribution we look at, right? If we're looking at the probability of one number, it would be 0 times the height of the distribution. Well, 0 times anything is always 0. Right? And the reason why it truly is because if it's continuous, and we could see, you know, 3.219567, then there truly is an infinite number of possible values here. Okay? So the probability of any one number, 0. Right? And with the uniform, we can kind of see, yeah, because my interval would start and stop at the same place. So the length of my interval there would be 0. 0 times anything is 0. All right. So if we kind of plugged into that form, right, it would always give us 0. Okay. Any questions on that? All right, I'll do one. Where are we at in time? I want to make sure I do. Okay, do a little more on the uniform. So I'm going to do one more thing. I'm going to keep using the same distribution. This uniform distribution to show you something. So let's say I had a uniform distribution, and it's, I don't know. Actually, let's change the numbers. Let's say it starts at 10, ends at, I don't know, 50. Okay. What would the height of my distribution be? How do we find the height? I said it was 1 over max minus the min, right? So 1 over, oh, not 40. I was thinking ahead. 50 minus 10, right? Maximum minus the minimum, or 1 over 40 will be my height. Let's say I wanted to find the probability of being between 15 and 20, or being between 35, and 40. Right? So if I go to find this area, right, what's the length kind of my rectangle there? 20 minus 15, multiplied by the height, which was what, 1 over 40? So 5 over 40, or what, 1/8, I don't know, which is what, 0.125? Am I doing math in my head there correct? Hopefully. So 0.125. Well, what do I know is, without doing any of the math, what do I know the area of that's going to be? It's the same. Why? The length of my interval is the same, right? 15 to 20, 5. 35 to 40, 5. So if I want the probability of being in either one of these ranges, 0.25 times 2 or 0.25 plus 0.25, right? So you don't have to just find the area, one interval. You could be asked to find what's the probability I'm in either one of these intervals. And we can actually relate this back to what we talked about with the union. What did we say? Let's see if I have enough room to write it. Is everyone okay with this? Can I erase this real quick? What do we say is true about the union? So the union of two events was just the sum of the two events minus the intersection, right? Well, if I have non-overlapping intervals here, what's the intersection? Yeah, there's no number between 15 and 20 that's also between 35 and 40, right? And so really, we've got mutually exclusive kind of events to find there. So all we have to do is find the probability I'm in A, add that to the probability I'm in B. All right, so if we have non-overlapping intervals, what we're really doing is find the probability I'm here or here, but it just becomes really easy because if they don't overlap, we know the intersection is 0. That's kind of where that idea, it's floating around in the background there. So we talked about all these things ahead of time because they still kind of float around in the background, okay? All right. Any questions on that or anything with the uniform or if I saw something different? And I will try to I don't know if I'll get done today. I have to do some traveling. I'm done teaching. Sometime this weekend, I'll try to record a short video over some uniform distribution kind of practice exam problems. So you'll have kind of a little video for those as well. Okay? Now, I think this stuff should be I think it's not too bad. I think this is way easier than Bayes' theorem, at least in my opinion. So hopefully, usually I see this kind of help add points to people's exams for these uniform questions. But if there's no other questions, I'll kind of switch over and do a few practice exam problems now. We're good with this? Now, one thing I will say, one more thing about the uniform before I forget. Be careful if you have a minimum that's negative, because then when you look for the difference, right, if I go from negative 10 to positive 10, if I just add them together, I'll end up with it's 0, right? I actually have to subtract the minimum. So it's 10 minus negative 10, which would be 20, right? The distance of that uniform is 20. But just be careful if you have a minimum that has a negative sign, it kind of gets a little tricky. Or if you're finding the mean, you're not subtracting it, it's 10 plus negative 10. All right, that is 0 because the mean should be 0 there. All right, so let's go to practice exam A. And actually, I also want to have on hand this formula sheet. So here's my formula sheet. Where's the practice exam? There it is. Practice exam A. Wait, is this the right one? There it is. I was going to say, I thought I had red. Okay. So let's go down here. Some ones I didn't do in those videos would be some more Bayes' theorem questions. So I would watch if you're wanting to kind of wanting more practice problems. Something that would be really good to pay attention to. Also, I have the exam written. So some of those examples I used in the additional video from last weekend that had more Bayes' theorem problems in it. Some of those examples would be really good to see worked through wink, wink, all right? So if you're kind of wanting to kind of more Bayes' theorem problems to go over, I would suggest looking at the problem in that video and trying to kind of work it out yourself, okay? So we'll do one here though that looks very similar to what you could be asked. So we've got steroid use in baseball, blah, blah, blah. So a manufacturer claims the probability a drug test shows positive given that an athlete is using steroids is 0.95. So let's just start writing out what we're given. So instead of using the board here, I'm going to type it out just so we can have, oops, why won't it let me edit this document? Protected view. Okay, there we go. So the information I was given here is the probability that given, right, and I'll use that language on the exam too, given an athlete is using steroids, so we'll say using, right, the probability that given that they're using steroids, the probability that the test shows positive, so we'll say probably that we see that the test come back positive is equal to 0.95. Right? It's the first thing we're given. So I'm just writing this out because I think it's easier to have it written out as a probability. The second thing is, however, the probability the drug test shows positive given that an athlete is not using is 0.01. So now we really have this exact same thing. It's just now it's the probability that they are not using. Given that they're not using, the probability the test shows a positive result or kind of these false positives would be 1%. Okay. This is a little small. Is that better for you guys in the back there? Okay. Those are the first two things we're given. We're then told a recent, Deadspin article says that if I choose somebody at random, the probability that they are just using steroids is what? 0.15. Okay. So those are the probabilities that I'm given, right? I might just write them out in order like that. Okay. Well, this one's pretty easy. If I might not need this information, but just to kind of be a complete example, show you a complete example and also show you how in some problems we might need it. I'm going to do like the probability tree, but I'm going to show you a slightly different way to do it instead of drawing it out as a tree, right? If I just write these three things down that I was given here, what's the probability that they're not using? Well, if the probability they're using is 0.15, the only other possibility is that they're not using, right? So the probability would just be 0.85? Yeah, 1 minus it, right? These two things would have to add up to 1. I'm either using or I'm not using. Right? What about here? I could say, okay, given that someone is not using steroids, the probability to get a positive test result is 0.01. So if I do the same thing and say, okay, given that they're not using, what's the probability that the test actually comes back negative? Right? What would that probability be? Yeah, right. If I have someone in front of me and I know that they're not using steroids, and let's say I give them 100 tests, right? And I know that one of those tests comes back positive, how many would have to come back negative? 99, right? And that's what we're saying. We're conditioning on that same person. It's almost thinking about, yeah, if they took 100 tests, the probability that it comes back positive is 0.01, or one of those comes back positive. What about the other 99 have to be negative, right? And so if we're conditioning on the same thing, we know that those probabilities would have to add to 1 as well. Then we could do the same idea here. If I condition on that the person is using, what's the probability that the test comes back negative? Well, here I was told if they're using, the probability it's positive is 0.95. So if they're using, the probability that, not the TET, but the test, the probability that the test comes back negative would just be 0.05, right? Now I know for the next 3 problems, I have all the information I could ever need, right? So I didn't necessarily have to get these. Potentially some of these problems might not need that information, but no matter what question I ask you now, you have the information you need to answer it. So we'll start with 13, just because I want to make sure that we get through it first, and then I'll kind of go back and do 10 and 11 if we have time. And we have 10 minutes, but I know this one takes a little bit of time to work through. So what I would do is, we have all this information up here. Write out what the question's asking you for. So given that the test comes back positive, what's the probability that the athlete is not using steroids? So what is given to us is what goes on the right-hand side of that vertical line. So we're told that given that the test comes back positive, right, what's the probability that the athlete is not using steroids? Okay? So that's what we're looking for. Now, if I look at my formula sheet, where is it? Oh, stop. Okay, so I'm going to go to my formula sheet here. If I want a conditional probability, I can rewrite that as the intersection divided by what I'm conditioning on. Now, the problem is, if I try to do that here, and I think about what my events are, I'd be dividing by the probability that just the test comes back positive. I don't have that. So usually, I mean, these, you can see from the practice exams, they kind of follow a similar order. But usually if you're asked for a conditional probability at this point, this equation is not going to work for you. But we know that we can break this equation down into Bayes' theorem, right? And so if I look at Bayes' theorem, I'm trying to find this conditional probability. Here's my S, right? So I could almost identify, here's my S, and here's my E, right? Here's my state of nature, here's my outcome for the test. I think the easiest way to do this, write this example out in the context of your, write this formula out in the context of your example, all right? So what I'm gonna do here is, okay, take the probability of S, my S is that they're not using, so not using, multiply that by the probability of E given S. Okay, my E is that the test comes back positive, given my S is that they're not using, right? And I'm just writing this out using my example. Now notice here, so that's my numerator. Right? And actually, no, I'm not gonna do that because it'll make it look goofy. So I'm gonna divide that by what's in the denominator here. Right? So what I'm gonna be dividing by, notice the very first part of this denominator is the exact same as the numerator. So I really could just write this exact same thing down again, maybe. Very good. And this is not looking pretty, so I'm going to hit enter here so it looks a little bit better. All right. So this, my numerator here is the very first part of my denominator. Okay? I'm then going to add to that, if I go back to my formula sheet, the probability of S complement times the probability of E given S complement. So in my example, my S complement, well, if S is that I'm not using, S complement would be that I am using. I'm going to hit enter here so this hopefully looks a little bit nicer. And this should be up here. So here's my S, here's my E, right? Here's my numerator. Maybe we can make this look a little prettier. Imagine this is a straight line for a second. I'm dividing by the denominator, right? So S complement is that they're using times the probability of E, so that's that the test comes back positive, given S complement. My S is that they're not using. We said S complement would be that they're using. So at this point, it's really just plugging numbers in. Once I have it written out in the context of my example, what's the probability someone's not using? 0.85. What's the probability that given someone's not using, the test comes back positive? Given that they're not using, given that they're not using, probably the test comes back positive is 0.01. Plug that in. Remember, the first part of the denominator is the same as what's in the numerator. So I just plug those numbers in again, 0.95, 0.01. The probability they're using, 0.15. Actually, I think I might have said that backwards. The probability they're not using is 0.85, right? I think I went up here and grabbed it. Probably they're not using is 0.85. Sorry, I just want to clarify that. Then the probability that given that they're using, the test comes back positive, given they're using, the probability the test comes back positive is 0.95. So this was an example where I didn't have to find any of these, right? I actually didn't have to do that, but I just wanted to be kind of complete in showing you how to do this. Also, you know, you can kind of imagine if I would have just switched one of these to, you know, given the test comes back negative, then I would have needed all these probabilities. Okay? But once I plug all my numbers in, then it's really just, you know, a little bit of multiplication and division, making sure I've got my order of operations correct. Any questions on that one? So I think if we plug in the numbers in here, do what? 0.85 times 0.01 divided by 0.85 times 0.01, and then we added to that. The probability of using was what? 0.15 times the probability that the test comes back positive. Was that 80%? Or am I remembering? 95%. Different example. Okay. So that's how you would do a Bayes theorem problem. Right? You know, it's up to you whether if it helps you. You know, I've got a lot of words going on here. For, you know, if it would have helped instead of not using, you put NU, or, you know, using was just you. You can do it that way as well. For some people, I think writing out the actual words, it does take up more space, like wherever you're working, but maybe it kind of helps you keep things a little bit more clear. It's really up to you. Okay? But I would suggest one thing that also helps is if I try to do this as like, the HIV example is a good one. Like if I write HIV positive and then I don't write that the test is positive, I just write positive in there. It's easy to like get mixed up. What's my state of nature? What's my outcome of the test? So usually for the test, the outcome of the test, I always like put the test is equal to this, right? Or jury equals guilty, or whatever the example is. Okay. I think we'll probably end there. These are just going to be not Bayes theorem problems, but we'll kind of start with these on Monday and revisit this. Okay. We still have a couple minutes. Are there any questions on this, or like what if something here changed, or yeah? So there will be 20 multiple. So there's going to be 19 multiple choice questions with one bonus question, so 20, and then there will be a short answer question that has 4, I think A through D. You have a slightly different exam than the other sections, so I'm trying to remember which one is which, but I think your short answer question has 4 components to it. Hour and 20 minutes. Right, so typically, when I'm giving these in person, and it's only 50 minutes, timing is not like usually a big issue for people, so I'm thinking this is more than enough time. One thing I will say is, just since we have a couple minutes, notice here, like where I say use the following information for the next 3 questions. I can get rid of it still, but what I did was just to not have any confusion about like what the next 3 questions are. I would have like you would see this, and then I would the next problem show you the exact same information, right? So you're going to see it like it's kind of all contained in each question. I did not try to trick you when I did that. I didn't change any of the numbers. You know, if you're seeing kind of this same table, it's still the same numbers. I'm just making sure that you can see it, so you don't have to like keep scrolling up and down on your computer. But I just wanted to say that like I'm not trying to trick you, not trying to change any of those numbers. It's just so that it's a lot easier for you to work on a problem and see the data right above you. Okay. Any other questions before we get out of here? Okay, like I said, it will show up Monday morning. You'll have all day Monday or Tuesday to kind of start it. I expect most of you will probably hold off until after we go through some more review on Monday. But if you run into any problems, feel free to email me as you're doing that as well. Okay. And over the weekend, if you have any questions, or I'll try to be responsive as possible. I'll be running around a little bit today and tomorrow, but Sunday for sure I'll be a little bit more responsive. Okay. All right. Have a good weekend. I will see you Monday. Well, not you guys. I'll see group 2 Monday if they want to show up.